Now we are going to look into another one of the important assumptions of the classical linear regression model when it is relaxed. The assumption I'm talking about here is that the variance of the error terms or the residual terms conditional on the x variable is equal to sigma square, independent of what the x variable value is. So no matter what the x variable value is, we are saying that the variance of the error term or the disturbance term ui is equal to sigma square. This is called the assumption of homoscedasticity or equal variance. When this assumption is not applicable, when this assumption is violated, we call it the problem of heteroscedasticity. So when it is homoscedastic, our assumption is, as we can see over here, that the expectation of ui square, basically we are talking about the variance of the error term, is equal to sigma square. As you can see, irrespective of what the I is, the variance remains constant and it is sigma square. When it is not satisfied, technically or mathematically, we can write it as the expectation of ui square is equal to sigma I square. So when it is u1, your variance term is sigma 1 square. When it is u2, your variance is sigma 2 square, and sigma 1 square, sigma 2 square, sigma 3 square and so on need not be equal to each other. So in effect, I am saying that the variance of the error term is different for different values of xi, and this is called as heteroscedasticity. If you remember, we talk about, I'm looking at the two variable case because that is easier to understand. The same understanding can be extended to multivariable case. So if you remember the two variable case, we had yi is equal to beta 1 plus beta 2 xi plus ui, right? So if you remember, we assume that our x variables are not random or they are fixed every time we do repeated sampling. So any variations in ui will automatically explain the variations in the observed yi around the mean estimated values of yi hat. Okay, what I'm saying is your beta 1 plus beta 2 xi can be written as yi hat. It is the estimated value or the mean value, estimated mean value of the y variable, and here I can write it as ui hat, right? So as you can see, or even if you write it as ui, that is also fine. So as you can see, since yi is the observed yi is estimated yi hat plus ui, the deviations observed in this term yi will be equal to the variance of ui. So you can look at that diagrammatically. If you see, it's a three-dimensional diagram. So you have x-axis, you have your y-axis. On your x-axis is income, which is your explanatory variable, and your dependent variable is savings on the y-axis. And you can see the first diagram is that of homoscedastic deviations. So as you can see, every yi term, every yi corresponding to xi is equally spread about the mean yi value. On the other hand, look at the second diagram. As you can see, as the income xi increases, the variance of the yi term also increases. Remember that variance means how far it is spread along away from the mean. So as you can see, higher, for if I call this value as the first value of x, the second value of x, and this is the third value of x. As you can see, for the term x3 or the third value of x, the distribution of observed yi from the mean value estimated yi is much larger than say x1, where the distribution around the mean is over a smaller range, right? And as you can see, x1, x2, x3, the distribution of observed yi values is different in each for each x. So we are talking about heteroscedasticity. Now let's have a look at the reasons and the sources of heteroscedasticity. What are the possible reasons that there is heteroscedasticity in the sample that we have at hand? One of the first explanations is that of error learning models. That is, as people learn, the errors in behavior will become smaller. So if in our model there is something where there is learning by doing, or where over time more experienced people will make lesser mistakes, and therefore the variance for more years of experience will be smaller than cases where there are lesser years of experience. So over time we would expect sigma I square to decrease. Okay, another example of models where you can have heteroscedasticity is say expenditure determining models. So I'm saying consumption expenditure is my y variable. It is being determined by the explanatory variable income. Now in such a situation, we know from empirical observations that at higher incomes people have more choice over how to spend their income, which is why there will be more variability observed in their behavior at much higher levels of income. Similarly, you can also look at a model where the y variable or the dependent variable is savings, and you are trying to estimate how is savings behavior dependent on income. Even here, we know from empirical observations that as the incomes grow, people have much more choice on the question of how to save, how much to save, in what manner to save, and so on. So even in models like that, we would expect that the variations in the savings behavior in my y variable will be greater at higher incomes. So as you can see, lower incomes, you have less variability in savings behavior, less variability in consumption expenditure behavior, but at higher incomes you can expect greater variability. So it could depend on the nature of the problem that you're studying. On the business side, several business economic models where you're looking at the dividend policies of companies and how it is being determined by the explanatory variable profits. Even here, it has been observed in various empirical studies that at higher profits, companies tend to exhibit greater variability in their dividend policies. So all these are dependent on the kind of model and the kind of problem that you're studying. All these are examples where we would naturally expect greater variations at higher levels of important x variables. Another source of heteroscedasticity is related to the data collecting techniques. If you have more improved and more sophisticated data collecting techniques and data collecting machinery, you can reduce the sigma I square. If you're an example would be if you're studying data given from banks where you have a mix of small as well as very large MNC banks. We know that the larger banks, the multinational company MNC type banks, have more sophisticated data processing equipment, and we would expect them to commit fewer errors than banks without such facilities. So again, you can think of models related to banking behavior or the behavior of banks in the money market and so on, where the sigma I square or the variance of the error term is not constant. Another important source of heteroscedasticity is the presence of outliers. Now, outliers are those values which are either very large or very small compared to the relative to the remaining observations in the sample. So inclusion of these outliers can dramatically change regression results, and this is more so if you have a very small sample size. So when your outliers are included in your sample data, you can expect heteroscedasticity. That is, the disturbance term will not have constant variance irrespective of the value of the x variable. Now, generally, these outlier terms, we say that these outlier terms which are very large or very small in value compared to the remaining observations in the sample, we consider them to be coming from a different population rather than the one from which the majority of the observations are coming. Another important source of heteroscedasticity is when the ninth assumption of the CNLRM, that is the classical normal linear regression model, is violated. Namely, by assumption 9, I mean the assumption that the model is correctly specified. If this assumption is violated, you can expect there to be heteroscedasticity. Again, in the Gujarati book, the example that they give is when you are estimating the demand function of any particular commodity. If you miss out on prices of related goods I mean either complementary goods or substitute goods, that is those goods who are a form of competition to our commodity under study. So if you miss out on the prices of these related goods, then the model has been misspecified or wrongly specified, and the residual terms or the UI hat terms of this wrongly specified model need not have constant variance. So misspecification or specification bias is another source of heteroscedasticity. Skewness in the distribution of one or more regressors can also be a source of heteroscedasticity. Typical examples would be when you're studying income distributions or wealth distributions, or even in countries like India, if you're looking at the distribution of land ownership. These are empirically and typically we know that these distributions are quite unequal. The Gini coefficient for these distributions in India in many cases is the Gini coefficient is very high, that is, there is high inequality. So if you have these skewed distribution variables as one of your regressors, it could be a source of heteroscedasticity in the sample or in the model as a whole. Then incorrect data transformations or incorrect functional forms, if they have been used in your model, they can also result in heteroscedasticity. So these are your main sources and reasons which can lead to heteroscedasticity in the sample that you have at hand.